Hello, am I audible and is my screen visible? Please let me know. Am I audible?
Yes,
Is my screen visible?
yes.
Okay, thank you. So good evening everyone. Welcome to the NPTEL live session for the NPTEL course Deep Learning IIT Ropar. My name is Learning-IIT. I am a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So this is my fourth live session. So we will discuss some questions on week 4 topics. So gradient descent and different variants of gradient descent algorithm and gradient descent with adaptive learning rates. These were the topics that were covered in week 4 module. So we will discuss some practice problems on these topics, and if you have any other questions or queries regarding these topics, please feel free to ask me during this session. Okay, so we will start solving the practice problems, and after that, if you have any other questions or doubts, you can ask me. So this is the first question. Statement is given that momentum based gradient descent algorithm and Nesterov accelerated gradient descent algorithm are faster than stochastic gradient descent algorithm. True or false? You can write your answers in the chat. So whether momentum based gradient descent and Nesterov accelerated gradient descent algorithm, these two algorithms are faster than the normal gradient descent algorithm or not. Dr. R. Kotishwaran says true. Okay. Anyone else? Immaculate Marcy says true. Kajal Gurnani says true. Okay, so the correct answer is true, that momentum based gradient descent and Nesterov accelerated gradient descent algorithms are faster than normal batch gradient descent or even stochastic gradient descent algorithm, because the momentum that we compute for the momentum based gradient descent makes it faster to convergence, and also for Nesterov accelerated gradient descent we compute those look ahead parameters which make it accelerated gradient descent, and also accelerates the process of convergence for the gradient descent algorithm. So the answer is true. Now question 2. Identify the technique that is used to achieve relatively better learning rate by updating using bunch of different values of eta. So eta is the learning rate. So this is the learning rate eta. So which technique is used to achieve relatively better learning rate by updating using different values of eta? Option A is bias correction, option B is line search, Option C is stochastic. Option D is all of the above. Kajal says option B. Correct answer is learning rate, line search. So in line search, what we do is that we keep a list of learning rate values. So we keep a list of learning rate values, for example eta 1, eta 2 up to eta, let's say L. And then during the gradient descent algorithm, for every eta in the eta list, we update the weight, we do the update w equals wt minus 1 minus of that eta into this. So this update is done for every eta value, and then we check for which eta value it is giving the best result, that is the error is reduced highest. So we pick that eta for that iteration. So for every iteration of the gradient descent algorithm, we run this loop for every eta in the list of the eta values. So this is line search. So we are basically searching which eta is best in every iteration of the gradient descent algorithm. Option B is the correct answer, which is line search. Question 3. Adagrad gets stuck when it is close to convergence. How does RMS prop overcome this problem? Option A is more aggressive on decay. Option B is less aggressive on decay. Option C is no decay. So decay of learning rate we are talking about in every case. So decay of learning rate. So how does RMS prop overcome the problem of getting stuck when it is closer to the convergence, which happens in Adagrad? Kajal says option B. Okay. Anyone else? Dr. R. Kotishwaran says option B. Any other answers? The correct answer is option B. That is less aggressive on decay. So ADAGRAD, in both ADAGRAD and RMS prop, it maintains a variable called VT, which is used to decay the learning rate. So in case of ADAGRAD, it happens like VT equals VT minus 1 plus sorry, not beta, gradient of W whole square, and then the weight parameters are updated as WT plus 1 is WT minus eta divided by root over VT plus epsilon WT. So this is the update rule used in ADAGRAD. So this is where the decay for the learning rate happens, eta divided by root over VT plus epsilon. So it starts with eta, but it is decayed after every iteration of the ADAGRAD gradient descent algorithm. And for RMS prop, only the computation for the variable VT changes. So it happens, so it so only change is this beta and 1 minus beta, these two parameters. So the beta is one parameter that is used to compute a moving average for the VT value. Instead of just adding this square of the gradient of the W, it computes a moving average over the gradient of WT squared. So this reduces this decay here. The decay is eta divided by root over VT plus epsilon. So this, because of this beta parameter and this expression, the decay of the learning rate is lesser aggressive, so that it can during the when it is close to convergence, it does not get stuck. The value of the learning rate is still substantial to drive the algorithm to the minima, which might be a problem in case of ADAGRAD, because the decay is so high that the learning rate becomes very small in case of ADAGRAD after few iterations, and it might not able to get to the minima. Now question 4. Which of the following gradient descent algorithm suffers from more oscillations? Momentum based gradient descent, Nesterov accelerated gradient descent, and vanilla gradient descent. Vanilla gradient descent is the normal gradient descent that we use. Kajal says option A. Immaculate Marcy says option A. Purna Pushpa Kala Suryamurthy says option C, which is vanilla gradient descent. The correct answer is option A, momentum based gradient descent. Suffers from more oscillations than the other two algorithms, Nesterov accelerated gradient descent and vanilla gradient descent. So in case of momentum based gradient descent, what happens is that it gains momentum as it goes down the error surface. So because the momentum is accumulated, so it can overshoot the minimum point, and then it will again have to come back, so it starts oscillating near the local minima or even global minima because of the momentum factor. So in a momentum based gradient descent, we accumulate the update values for every iteration, so the updates can become very high, and if the update value is very high, then it can overshoot the minima point. So that is the problem with momentum based gradient descent, that it can suffer from more oscillations near local or global minimum. Question 5. Identify the advantages of Nesterov accelerated gradient descent. More than one option may be correct here. Option A says corrects its course quicker than momentum based gradient descent. Option B says oscillations are smaller. Option C says chances of escaping the minima valley are smaller. So multiple options may be correct in this question. Kajal says all options. Okay. Immaculate Mercy says A and B. Any other answers? Correct answers are A, B, C, all three. So in Nesterov accelerated gradient descent, the first option is that corrects its course quicker than momentum based gradient descent. So it uses the look ahead parameter for the gradient of the weights. So using that look ahead parameter value, it can corrects its course quicker than momentum based gradient descent, whereas momentum based gradient descent will accumulate the value of the updates and it can overshoot the minima point, it can miss the minima point. That problem is corrected here. And option B says oscillations are smaller. Again, because of that reason, oscillations are smaller, that the steps are not that high anymore, and it uses the look ahead parameter value of the gradient of the parameter. So oscillations become smaller, and chances of escaping the minima value are smaller. So if oscillations are smaller, there are lesser chances that it would escape the minima point or the minima value. So all three options are correct here, A, B, C, for Nesterov accelerated gradient descent. Question 6. Consider the following functions: x square, natural log of x plus 2, e to the power 2x, and x cube. There are 4 functions. Which function has the steepest slope at x equals 1? Sorry. So you have to find the slope for each of these 4 functions at x equals 1, and then you have to find which has the steepest slope at this point, x equals 1. Kajal says option C, which is e to the power 2x. Immaculate masses says option D, which is x cube. Vandana Mahajan says option D. So for this question you have to compute the derivative of each of these functions at x equals 1. So for the first function x square, the derivative is 2x. So at x equals 1, the value of the slope would be 2. So similarly for ln x plus 2, value of the derivative is 1 divided by x plus 2. So at x equals 1, the value of the derivative is 1 divided by 3. Then for the third function, so it will be 2 into e to the power 2x. So at x equals 1, the value is 2 into e squared. And for the final function, last function, dx of x cube would be 3x squared. So at x equals 1, the value of the derivative would be 3. So this value is so e is 2.7, around 2.7. So we have to take the square of this and then multiply it by 2. So certainly this value is more than 3. Obviously square of 2.7 would give you around 7 or 8. So multiplied by 2 would be 14 or 16, between 14 to 16, which is certainly greater than 1 by 3 or this 3. So this value is the highest among all these slopes, 2 into e square at x equals 1. So correct answer would be option C, e to the power 2x. Two of you have said option D. Possibly there was some mistake in the calculations. So I hope the values I have calculated are correct. So if it is correct, then option C would be the correct answer here. So is there any doubt in this question? Okay. Now question 7. Which of the following is a variant of gradient descent that uses an estimate of the next gradient to update the current position of the parameters? So options are momentum based gradient descent, stochastic gradient descent, Nesterov accelerated gradient descent, and option D is ADA-grad. Kajal says option C, Nesterov accelerated gradient descent. correct answer is option C, Nestor of accelerated gradient descent. So it uses an estimate of the next gradient to update the value of the parameter. So it computes that look ahead of the gradient of W. So it computes this thing. So this is nothing but an estimate of the gradient next gradient value. So correct answer is option C. Now question 8. What is the role of activation functions in deep learning? Option A says activation functions transform the output of a neuron into a nonlinear function, allowing network to learn complex patterns. Activation functions make the network faster by reducing the number of iterations needed for training. Option C says activation functions are used to normalize the input data, and option D says activation functions are used to compute the loss value. Kajal says option A. Vandana Mahajan says option A. The correct answer is option A, that activation functions transform the output of a neuron into a non-linear function, so that the neural network can learn complex patterns or complex functions. Without activation functions, it's just matrix multiplication. If a linear matrix multiplication, it would not be able to model any non-linear function. So the activation functions bring the non-linearity into the neural networks. So option A is the correct answer. Now question 9. For the ADA-grade algorithm, consider the values of different parameters. So first is the gradient of Wt is 0.4. This is Vt minus 1. So it's not Vt, it's Vt minus 1 is 0.2. This is epsilon, which is equal to 0.1, and eta is 0.1. And the current weight value or the parameter value is 1.0. Wt equals 1.0. What is the updated weight if we use ADA-grade algorithm here? So you have to find out Wt plus 1. So you have to find Wt plus 1 using these different parameter values, and you have to use the ADA-grade update rule here. I have not received any answer in the chat yet. So the calculation might be a little tedious. So if you have followed the lecture material or the video lectures, you would know that the ADA-grad update rule is something like this. So VT is updated as VT minus 1 plus gradient of WT whole square. So VT minus 1 is given in this question. So first you have to compute VT just by adding this gradient of WT squared. So this gradient of WT is given here 0.4 and VT minus 1 is given here, so that you can compute VT from that. After computing VT, now the weight values would be updated. WT plus 1 is updated as WT minus eta divided by root over VT plus epsilon into gradient of WT. So after you compute VT, now you just have to plug in these values: eta, VT and epsilon. All these values are given. Eta, epsilon, eta and VT comes from the first equation, and WT is also given as 1. So you just have to plug in these values here. Kajal says 0.9412. Yeah, so the correct answer is 0.9412. So Kajal's answer is correct. So you basically have to use these two equations. So for every iteration in the ADA-grad algorithm or the ADA-grad update rule, first the VT is computed from VT minus 1 and gradient of WT, and then WT plus 1 is computed from WT, eta, VT, epsilon and gradient of WT. So you have to just put these values into these two equations and you will get this updated values of the weights. So I hope these calculations are correct. You can check it later on. So is there any doubt in this question? Question 10, again almost on the same values of different parameters and hyperparameters. Now for RMS prop algorithm. So in the last question we did it for ADA-grad algorithm. Now you have to do it for RMS prop algorithm. All these values are same. The extra hyperparameter that we have is beta equals 0.9. So this beta was not present in ADA-grad. So this is a new thing in RMS prop. So this beta has to be used, and eta and epsilon and current value of the weight parameters are given. You have to compute the updated weight, which is WT plus 1. So everything remains almost the same, just the computation of VT changes because of this beta hyperparameter in RMS prop. Otherwise everything remains almost the same. Kajal says 0.9264. Okay. Has anyone else computed this? So in RMS prop, the update rule is almost the same as ADA-grade. Only change is in the update of VT. So VT is updated as VT minus 1. Beta into VT minus 1 plus 1 minus beta into gradient of W t whole square. So this beta and this beta and 1 minus beta, these two factors were not present in the ADA-grade. It was only Vt minus 1 plus gradient of Wt's whole squared. So these this beta and 1 minus beta, these two factors are present here. And after that, the update for the weight values remain the same. So this remains the same as ADA-grade. So only the value of the Vt changes because of this beta and this 1 minus beta factors. So beta value is given here 0.9. So the beta value is given here 0.9. Other values are also known. Vt minus 1 is given as 0.2 and this gradient of Wt is given as 0.4. So using these values you can first compute Vt, then this value of Vt, eta, epsilon and gradient of Wt can be used to compute the updated parameters Wt plus 1. So if you put these values, you should get something like this 0.911. Kajal is saying 0.9264. So I have to check whether the calculations are right or not. But this is the process to compute this. You can check whether the values are computed correctly or not. I might be wrong here, but this is how you have to compute the Wt plus 1. Is there any doubt in this question? Okay, so these were the practice problems that I wanted to discuss in this live session. And now if you have any other questions or doubts or queries, you can ask now. How will you calculate the square root? So in the exam would most probably be computer based. If it is computer based, you will have a built-in calculator in your computer which you can use for mathematical calculations. So it will be a scientific calculator application in the computer. You can use it for any kind of complex calculations. Is there any other questions? Okay, if there are no other questions or queries, then we can end this live session now. Thank you everyone for joining. We will again meet next week for the 5th live session. Thank you everyone for joining.